Hi guys, today we're on Unit 11, Lesson 2, and we're going to be talking about the derivative today. So yesterday we presented two interpretations for the quantity represented by the limit as x approaches c of f of x minus f of c over x minus c. We said this could represent the slope of a tangent line at a point and the instantaneous rate of change at a specific point. So you've got to understand that these two things mean the same thing, and we find it by evaluating that limit. This particular limit is one of the most fundamental concepts in calculus and is called the derivative. Yesterday, we found the slope of the tangent line or the instantaneous rate of change at a specific value. Today, we're going to derive a formula to find that derivative, but then we can use it as a function. So the derivative is a function that represents the slope of the tangent line for any given x value. So let's kind of go back to yesterday for one moment. And if we're dealing with some given function, and we want to find the slope of the tangent line at a specific value. Remember, the answer we get is representing the slope of that line, the instantaneous rate of change at that value. Yesterday, what we did was we took a point that was further away and we brought that point closer and closer and closer to x until eventually it was right so close that the slopes would be the same as if you had 2 points. And we evaluated it like this. Today, we're going to generalize this formula. So instead of using c and x, we're going to take our slope formula and we're going to do a couple of algebraic manipulations with this formula. Okay. So basically, yesterday, what we were using was this point would then be c and f of c. This point up here is x and f of x. So now instead of using c and x, we're going to call this c value, we're going to start at x. And this value over here is going to become x plus h, where h is an amount. So if we move this point closer, this means h is going to 0. For instance, if I start at the point 1 and 1.5, my h value is 0.5. But if I start at the point 1 and go to 1.25, h is getting smaller. So as h gets smaller, the amount we're adding to x, that x value is moving closer. In essence, this point's moving closer and we'll get the same slope. So using function notation now, let's kind of see what happens. This point now becomes x plus h as my input or my x value. So my y value is f of x plus h. If my x value is x, now my y value is f of x. So we're going to take, and we're going to rewrite that slope formula. Now, instead of evaluating the limit as x approaches c, remember, we're evaluating the limit as h approaches 0. y2 minus y1, right? F of x minus f of c. Oh, sorry. So we did y2 minus y1. Now we're going to do x2 minus x1. x2, x plus h minus x1, which is just x. And if you think about it in the denominator, I have x plus h minus x, the x's are going to cancel. And our slope formula now becomes the limit as h approaches 0 of f of x plus h minus f of x over h. The notation we use when we're representing a derivative is f prime of x. So now when we find a derivative or a slope of a tangent line, we're going to remember to use f prime of x in our answer. There's other notation as well. We can sometimes just say y prime. We can sometimes say dy dx, and we're going to use this a little later on in the course. Okay, so I'm just kind of introducing that notation today, but for our purposes, we're going to kind of stick with this guy and this guy at this point in time. Okay. A couple other little things. Differentiation. If you hear me say the word differentiate, that means find the derivative. And just, once again to remind you, when you find the derivative, we have a function that gives the slope of the tangent line at any given x value. I'm going to go back up here for one moment. This limit, this guy here, is known as the definition of the derivative. Some people call it the limit process to finding the derivative. So, just be aware of little quirky things that happen when we're moving through this class. Right. So we have it on the page with our examples. Remember, when we use the definition of the derivative, the limit as h approaches 0 of f of x plus h minus f of x, we're finding a formula for the slope of the tangent line at any x value. So yesterday we did a few examples with f of x equals x squared. Remember? I think we found the slope of the tangent line when x equals 1, and we got 2. I think we did another one, but it doesn't really matter. Remember, you're getting that. So we used the limit process using the limit as x approaches c. Okay. Today we're going to find the derivative using the definition of the derivative, and then we'll talk about what the results mean and how they're the same and how they're different. So if f of x equals x squared, and I want to use the limit process, I want to use the definition of the derivative. I'm going to start by setting up my derivative. F prime of x equals the limit as h approaches 0. Now, what is f of x plus h? Think about it. We did this earlier in the year. If f of x equals x squared, f of x plus h is what we get when we evaluate that, right? Replace x with x plus h. Just going to give myself a tiny bit of room. So this is going to be x squared plus 2xh plus h squared. We need to memorize this. So I'm going to put f of x plus h, the result I got, in this spot. That's my f of x plus h. Now I'm going to subtract f of x. And I'm writing it out the long way for this example, and then we'll maybe take some shortcuts as we move through. I'm just going to clean this guy up a little bit now, because what do you notice? When I plug in 0 for h, I'm going to get a 0 in the denominator. So I know I'm going to have to do some work in the numerator. x squared plus 2xh plus h squared minus x squared over h. We're going to cancel the x squareds. And if you look at what you're left with, I can factor an h out. My h's cancel. And I'm going to reevaluate. Right now that I simplified it, we're going to reevaluate this. And now instead of plugging in 0 for x, remember, now it's h goes to 0. So we want to remember when we evaluate this, it's 2x plus 0. So our answer is 2x. What does this mean to us? F prime of x, which is the derivative of x squared, is 2x. And this is a rule. I can use this now. If I go back up here, if I know f prime of x equals 2x, if I want the slope of the tangent line when x equals 1, I can just plug 1 into this rule, and that's my slope. So this formula now, this answer is a rule to find slopes. What if I wanted the slope at -1? Well, f prime of -1 equals -2. What if I wanted the slope at 0? I would plug 0 into the derivative. And it's kind of easy to see on here that your slope is 0, right? When x equals 0, the slope of the tangent line is 0. Okay, so this now is huge. This is important. It might take a little bit longer in the beginning, but if you need to evaluate, right down here, now we have a rule that we can get the derivative function, or we can get the derivative or the slope of the tangent line at any given point using this rule. Today, really all we're going to practice is setting up the definition of the derivative. Of course, I kind of went into my other problems, so I'm just going to make my work a little smaller so that I have room to work on this next example. I'll try to make it a little neater this time. All right, so anytime I'm going to set up my definition of the derivative, my limit definition, if I'm given a function, I know I'm going to have to find f of x plus h. So I usually kind of do that right away. Once I have that, then I set up my limit. Remember, the limit is f prime of x equals the limit as h approaches 0 of f of x plus h, right? 3x plus 3h minus 4. Now I'm going to subtract f of x. Okay. And if you want to save a step, you know you're subtracting a quantity. So I'm just going to negate each term when I put it there. Just saves me one step of simplifying or writing. All over h. F of x plus h minus f of x over h. You're always going to get a 0 in the denominator, so you should always work on cleaning up the numerator. -4 plus 4, the limit as h approaches 0 of 3h over h, and my h's are going to cancel as well. So the limit as h approaches 0 of 3, well, I remember the limit of a constant is a constant. So this derivative is just going to be 3, which means f prime of x equals 3. No matter what value you plug in for x, your slope is 3. Again, we talked about this yesterday. This is a line. 3x minus 4. So what this means is no matter what value I plug in, the rate of change, no matter where I go on the function, is 3. The slope is 3 because the slope of the line is 3. Notice if we go back up into our parabola, our slopes change as we move around. The slope is not constant. That's why we use that rule, that formula. Okay, let's go back to another parabola. F of x equals 3x squared plus 1. We're always going to be starting when we're using the definition of the derivative by having to set up that x plus h portion, so we might as well get it in the very beginning. 3x plus h squared is x squared plus 2xh plus h squared plus 1. Distribute. So here's my f of x plus h. Here's my f of x. Those are the two pieces that have to go in the numerator. F prime of x is going to equal the answer I get when I evaluate this limit. F of x plus h minus f of x, remember, negate each term, all over h. So you can start cleaning up now because we know we're going to get a 0 on our first plug-in. We're going to get a 0 in the denominator. My 3x squareds are going to cancel. My 1s are going to cancel. I'm left with the limit as h approaches 0, 6xh plus 3h squared over h. Factor out. Oh, I could have factored out more. Sorry. That's okay. The h is what's important. The h is what you want to cancel. So f prime of x is equal to the limit as h approaches 0 of 6x plus 3h. When you evaluate that, remember, you're substituting 0 for h. So the derivative is 6x. And this is a rule to give me the slope of the tangent line at any given point on the parabola. On your homework tonight, you might be asked to evaluate a couple of different ones. So I could do f of -1. And so that would be the slope of the tangent line at the point -1, whatever that point is on the curve. Okay. This one's going to be a little bit annoying. Oh, I got a little extra f there. F of x equals x cubed. Again, we have to find f of x plus h first. This is not going to be fun. And in a couple of days, we're going to learn a shorter method. But for right now, this is what we have to use. F of x plus h. So x plus h cubed is x plus h times x plus h times x plus h. Terrible. I'm going to kind of, I'll leave this one alone. I'll FOIL out these two guys, but hopefully you know that this is really just x squared plus 2xh plus h squared. Now we're going to work it through. So I'm going to distribute x cubed plus 2x squared h plus xh squared. Now I'm going to distribute my h plus x squared h plus 2xh squared plus h cubed. Clean this guy up. X cubed, 2x squared h and x squared h gives me 3x squared h. Xh squared plus 2xh squareds gives me 3xh squareds plus h cubed. There's my f of x plus h. There's my f of x. We're going to substitute these values into our limit definition. F prime of x is going to equal the limit. I already know I'm not going to have enough room. F. The limit as h approaches 0 of f of x plus h minus f of x over h. I'm going to cancel my x cubes, right? Because I know I'm going to get a 0 on the bottom. I have to clean up the top. The limit as h approaches 0. And if I notice here, I'm going to have an h in each term. So I might as well just factor that out right now. 3x squared plus 3xh plus h squared all over h. My h's cancel. My limit as h approaches 0, 3x squared plus 3xh plus h squared. If I plug 0 in for for h, and I evaluate this term is going to go to 0, that term is going to go to 0, and my derivative function is 3x squared. What does this mean? Again, this is a slope to find the tangent line at any specific point on your given curve. Okay. This one was a challenge, and I think we just did one of your homework problems, so that's that's a good thing. But again, practice, and we're going to work on this again tomorrow with some different types of functions. Okay. The ones we were dealing with today are all polynomial, but remember, we've studied radical functions, we've studied things that are complex fractions. So we have to make sure that we understand how to do all of these different algebraic derivative rules. Okay. All righty, guys, do your homework and see you again soon. Thanks.